This is lecture 3. This is a second example, and I made this example simply because it has, our previous examples did not have an example where we're actually writing a RAM. So this example is requires that the RAM be written, and it's once again, it's pretty simple. It has a RAM. The idea is to read through that RAM, find the largest value in that RAM, and clear that value. So it's kind of a multi-step process on this. What I'm going to do here is I'm going to be waiting for a go signal. That's going to be one state. Next thing I'm going to do is I'm going to be searching for the output, the largest value, we'll say, of in the RAM. And once I find that large value, after I go through the whole entire RAM, I'm going to I'll have the largest value, and I'm going to need to clear that value at that given location. So this means a couple things. One is there's three things I need to do. Is I need to wait, I need to search, and then I need to go write. So the implication there is that there are three states in this, and there are going to be three states in it. So this circuit gets a little bit more complicated, but once again, this is the first video where I'm hoping that you kind of get a good feel for what's going on, get an intuitive feel for what's going on, and what some of the modules are required in this thing. So it has a RAM, which means we're going to use a counter to drive the address of that RAM. So that's what we always do. We're going to do that again this time. But there's two things you need to notice about this problem. One is anytime I'm comparing something, essentially in this circuit I'm comparing two different values of the one of them being the current RAM output, and the other one's being kind of a running, I don't want to say running total, but running greatest thing I've seen so far, greatest piece of data I've seen so far. So the implication there is I need some type of memory for the data, and that memory is simply going to be a register. In this case, it's 8-bit. It's just going to be an 8-bit register. Also, I need to be able to store the address of that large piece of data. Okay, so once again, I need to have another register. The other register simply is going to be storing the address of the large piece of data. So this is a very generic algorithm. What it's going to do, once again, the storage is storing the data and storing the address of that data. And so when I'm done with the algorithm, I can come back and go back to that address and clear that data. So a couple of implications here is the RAM is going to have two different address values. Essentially, I'm going to have to choose between two different address values. One of them is going to be the output of the counter when I'm searching the RAM. The other one is going to be the output of that register that remembers the address of the large value. So I'm going to need to write the RAM, and so I'm going to need to go back and load that, use that address of that data as an address of where I'm going to clear. And so once again, there's going to be a mux in there because I have to once again choose between the counter output for the address and the register output for the address. Other things I need in this circuit, obviously I am going to be comparing the current value with the previous value, so I need a comparator. And of course this is going to be controlled by a state machine as well. So there's anytime you're doing algorithms such as this, it simplifies the hardware if you take a generic approach. So what the approach I'm taking in this thing, I'm looking for the largest value. So I am going to treat all the register values as equivalent, in that I'm going to clear that large value register. So that value's at 0, and it's going to be comparing the 0 address, the data at address 0 for the first time. So that I'm not going to try to load two different things. I'm going to compare the first thing to 0, And so that kind of genericizes the algorithm. I'm not going to try to get fancy and put an extra state in there to load the first value and compare it to the second value. I'm not going to try to do that. And there's also an issue here of I think this algorithm will only work if there's at least one non-zero value in there. So I actually stated there's one non-zero value in there. So this circuit in general doesn't have an output, which I felt was kind of uncomfortable. So I actually made an output for it, and I'm going to put that down. This is my top level circuit, and what I have here is an output, just an LED output or something like that, a done signal. So when it's waiting, the done is on, otherwise the done is going to be off. So it's really simple in the state machine. So this thing has a clock, and this thing has a go signal. And I believe that's the high level top level diagram, high level interface. And I think at this point, I think we're going to go ahead and list what circuits we need in here. So we got a RAM, which means we also need a counter, C-U-N-T-E-R. This counter, it's going to be a 5-bit counter, simply because I need to address 32 different things. I also need a register for a data register, so that's going to be 8 bits. I need a register for an address. That register is going to be, this is storing the address, which is going to be 5 bits. And I need a comparator. And it's going to be, well, essentially it's an 8-bit comparator, so we'll put that down. And lastly, of course, as in all these problems, I need some type of controller circuit, which is the state machine. And I think that's all I can think of right now. We're going to go ahead and jump into this in the next experiment. Once again, I'm going to have to do it kind of fast so I don't take too long and YouTube hates me.